Welcome all to today's ASRG World Webinar. We have the 29th of July 2021 and we are streaming from Stuttgart in Germany. Thank you for being with us. My name is Sven Schran and I am coordinating with ASRG the European locations. The Automotive Security Research Group is now 4 years old and we are a non-profit organization which provides a platform for the automotive security industry as well as related academics or organizations to share knowledge, build powerful networks and valuable collaborations. This community is for you and it's based on volunteer support. If you want to know more details about ASRG, please check out our website at www.asrg.io. Maybe you have an idea for a nice project and look for partners to realize it. You would like to start your own location, you have an idea about a service ASRG could provide, or you simply know a great organization which could partner with ASRG. We are open to hear each idea you have in mind and would like to discuss how ASRG can support. Don't hesitate and get in touch with us. You quickly can send us an email with your thoughts to hello@asrg.io. So this is now enough from my side and I don't want to keep you tortured anymore because I'm sure you are waiting very curiously for our main presentation today. Like every time, in case you have questions during the presentation, please write it into the chat window. After the session, we will have some more minutes for questions and answers. And now it's my pleasure to welcome Dmitry Janushkevich, Senior Consultant at F-Secure Consulting. Today, he will give us some insights about U-boot versus security. And now, I would like to hand over to Dmitry. The virtual stage is yours.
Thank you very much, Sven. I will be happy to take the stage. Welcome everyone again to the to my talk about U-boot and its security. And maybe a few words about myself. I work on computers or against computers, if you wish, for the last 20 years. I am a senior security consultant with the product security team at F-Secure, and about half of my work, give or take, is ECU security assessments, especially IVI units, which have a lot of different interactivity features. I have keen interest in secure boot, in fault injection attacks, in side channel analysis attacks, and occasionally do some cryptography. Well, you can say it hacking, but still I have quite some interest in that topic as well. And I am always happy to chat. Please feel free to reach out at infosecdj via Twitter at any time. I'll be happy to talk to you about anything security. But that's the talk is not about myself. So before we proceed to the meat of the talk, I'd like to give you first some context about U-boot and its place in the overall system architecture. So as you know, automotive networks today are rather complex. On the picture is not today's network, it's rather dated, I would say, but still it's kind of representative of what one might find in each and every automobile today. It's a lot of networks connected with a lot of different ECUs, which are basically small little computers in your car. And each ECU has lots of different software blocks, of course, different little parts which someone has written. Of course, there's some hardware as well, which underpins it, but on top of hardware, there's some basic drivers. There are some complex drivers supporting, for example, communications or graphics. There is also some applications and diagnostic functionalities, as well as a DOS scheduler. But what's interesting, there is also a nice black little box called bootloader as well, which we will talk about a bit later. But in recent years, I think it's a well-seen tendency that Linux is starting to be seen in the automotive world quite a lot. And there are at least two major initiatives which are well known, which are GNUI as well as Automotive Grade Linux. And it is, I think it's well founded, because if we go a bit back, Linux takes care of quite a few blocks of this generic ECU architecture, if you wish. It takes care of almost everything apart from the application diagnostics and the bootloader parts. I mean, in the best case scenario, your SoC vendor will be able to ship you the drivers for each and every peripheral, so you don't have to write them all from scratch, and you get Linux for free. So that's that. But I think in most of the ECUs that we see where Linux is used, there are kind of two kinds of ECUs that it fits the best. First one is infotainment units, which are typically exposed to malicious input, of course, because anyone can plug anything if they are in your car. But that also includes malicious car owners as well, which buy your car and want to steal your IP from your unit, which you designed. What's also interesting is that it connects to internal networks, of course, because everything in the car connects to internal networks. And it also runs feature-rich applications which enlarge the attack surface sufficiently to make it feasible to attack the unit from that side as well. The second one that is interesting is the telematics units, which we see in more modern cars. These are exposed to external networks. Typically, they are connected via some form of wireless connectivity, such as Bluetooth or in fact 3G or 4G, or nowadays 5G as well. It also connects to internal networks, and it also tends to run feature-rich applications. In these two cases, it is rather clear that there is high risk, and it calls for higher security as well to mitigate it. But to actually, boot Linux, you need to do quite a lot of tedious tasks, such as, bringing the platform up. Somehow you need to also to load the Linux kernel. You also need to load the initial RAM disk, and you also need to pass control to Linux kernel. And last but not least, you would also need some kind of development access and tools to manage all this zoo. So enter U-boot, or in fact, das U-boot. And if we look at the feature list, it is happy to take care of most of these problems. It supports quite a lot of existing CPU architectures and quite a few of not so mainstream ones. It has some support for bringing your platform up. Typically, there is some kind of pre-existing code for this CPU or this family of SoCs or this board that you have in the main U-boot tree, or this can be also supplied by your SoC vendor too. U-boot handles putting the Linux OS natively, so you don't have to do pretty much anything except building your OS image and handing it to U-boot. It also has scripting support, so you can script your boot process as much as you would like if you have some custom needs for that. It also provides secure boot support. So if you have higher security needs, as we've seen in the case of IVI units and in the case of telematics units, you can protect your system in that way too, which is, by the way, highly recommended. And U-boot also provides a lot of storage drivers, a lot of network boot functions. It also gives you console access, so you can interactively communicate with U-boot in case you need to test something, for example, during the development process, and many, many more features. And I really believe that U-boot is truly the universal bootloader, which is coincidentally what U-boot stands for. But I hope this gave you some context. as to what U-boot is and how useful it is, and why we see it all over the place in embedded world. So I think we should probably follow on with the actual U-boot problems which lead to security compromises. And well, this is not really U-boot specific. However, this is a problem of likely all software that you could possibly find in today's systems, which is outdated versions of software, in this case, U-boot itself. This is mostly because when you decide on a given SoC, you also decide on a given SoC vendor and the software packages that they provide, because you don't really want to spend effort on developing everything from scratch yourself. This is why you use U-boot, and you don't really want to spend effort on extending U-boot for your SoC vendor too. So you take what they provide you, and typically they provide something, which is great, of course, but it tends to be, well, let's say frozen in time. So they take a given U-boot version, they modify it somehow, and they give it to you. It also so happens that the SoC vendors are not too keen on updating their U-boot versions, because it takes effort to support everything between versions and so on. And maybe it's done once in every 2-3 years, and then that works. However, we all know that modern security is a rather fast-paced industry. So bugs come out, or other bugs are found out on a, well, let's say weekly basis, or maybe monthly basis, but it's much, much faster than the usual SoC vendor is willing to update your U-boot version. So the end result is that you end up with a really outdated and old version of U-boot. And in the best case, you get a security patch from your vendor. So this is why well, at least we used to see U-boot versions from 2014, for example, which is not the most recent one, so to say. So what the attacker would do is they would just develop an ND exploit for a given CV that is publicly known. They make the device run it, and they get to execute arbitrary code, which is the ultimate goal of any attacker. But this is not the only problem, of course. So moving on to the beloved probably feature of any hardware developer is extra boot options, which really save your day when something goes really wrong. So you would like to recover your system, and you're not really keen on desoldering the eMMC chip you have on your pretty board. So the way this goes is that normally a system boots from a one onboard memory type. We'll say it could be eMMC, it could be serial SPI flash, it could be anything, but usually it's only one. But as a development artifact, it also happens that options are left for booting from external USB, for example. It could be a micro SD card, it could be TFTP, NFS, and you name it. It could be configurable via, for example, onboard jumpers, which are soldered on the factory, or it could be just jumpers which you can reconfigure manually if need be, or it could be a dip switch or something like that, or it could be also probed automatically. So you insert a USB, then it boots from USB. If there is no USB drive inserted, then it looks that there is no drive, and it boots from the internal eMMC and so on. What's great is that you don't really need to desolder anything. It just, you insert properly formatted media, you put what you want to boot on that media, and you try to boot it. If you get lucky, you get to execute arbitrary code again, which is great. The great feature of a U-boot is its scriptability and its interactive console access, but it also spawns a really, really great host of problems. which we will look at now. And the first and the probably the most widespread one is the ability to interrupt the auto boot sequence. And the auto boot sequence is basically a short script that the U-boot runs, and the script is provided as a simply as a boot CMD environment variable. So you can put anything you like there. And when autoboot is active and when interruption is enabled, you see the nice pretty message that says hit any key to stop autoboot. And when you hit any key to stop autoboot, autoboot stops. Nice and simple. What it does, it interrupts the autoboot sequence and it pops the console access, interactive console access, and you can enter any command you'd like, which ultimately results in execution of arbitrary commands and as follows execution of arbitrary code too, because you can read and write memory using built-in U-boot commands, and that's the end of the game. The next one, as I mentioned, there is something called environment variables. Well, this is it. It's a set of key equals value, basically pairs. And they can be present in non-volatile memory, they can be compiled into the U-boot image itself. It can be a file somewhere on the file system. It can be stored in a given region of SPI flash memory or eMMC memory. There are quite a few options that modern U-boot provides as to where it will load its environment variables. The problem is that it is only integrity checked with a CRC32, and that's basically it. And we have never ever seen it being encrypted and or signed, which means that for an attacker which can actually get access to the location where it is stored, be it in SPI flash or a file on the built-in memory, they could go ahead and manipulate these environment variables. And the most interesting one is, as I mentioned before, the boot CMD one, which is the auto boot script. So it leads to the same outcome. You can execute arbitrary commands, and again and again you can get to execute arbitrary code, which is always great. It is also interesting and probably not as well known that U-boot tends to fail open when something goes wrong. So as I said before, the boot process of U-boot is typically implemented as some form of a script, be it in a boot CMD variable, or be it in some other environment variable, or be it really hard-coded in the source code of U-boot if you modify it. But the problem is that when this script finishes execution, U-boot enters the console loop, which means we see a nice interactive prompt again, and we can enter arbitrary commands, and we can execute arbitrary code, which is always great. What you do is quite simple. You just make the boot process fail. You can, it depends, of course, on the actual memory type that you have and the actual boot behavior of your U-boot instance. But you can remove the flash chip from the board, for example, or you could short the chip select pin to disable access to the flash memory, or you can be all kinds of creative, but the goal is to make sure that U-boot does not do what it wants to do. And if you do that, then U-boot fails open and you get to your goal. Nice and easy. The next problem is, it's not a problem as such, but it is a feature that is to some point a little bit obscure and not as well documented as we would like it to be. It is verified boot, which is an implementation of a secure boot, chain of trust in U-boot. And the result of the feature not being as well documented as it could be is that we quite often see that even though the images are signed, it is not a hard requirement. So they can be signed and the signature will be verified, but if it's not signed, then it's okay. So what is fit images? Basically, it's a well, you wouldn't say it's an abuse, but it's another use of device tree blobs to store kernel images, to store file system images, as well as configuration data. So you can have all your OS minus maybe some on-disk data, mutable data in one big image, and this image can be signed, and the signature can be verified as well. So there is a tool called Make Image, of course, which does the signature. But what it also should do is to add a signature node to the U-boot device tree blob, which is integrated in U-boot. And this step is often forgotten because it's not really obvious how to do it, and it kind of well, let's just say people tend to forget it because it just works. It doesn't complain that the signature is not required, but it also verifies it. So which means that it could mean that no signature node is no checking, so you can remove it from the fit image. For that, you need, of course, a tool to manipulate fit images, but that's a solved problem. And that means that in the end of the day, you can put your crafted images, which you make by removing the signature node, and that's about it. It's basically as easy as it gets. So you extract your image from the flash memory, you remove the signature node, you tamper your whatever you like on the target system in that image, you put the image back, you put it back on the flash, and bam, it boots, and you get to execute arbitrary code as well, which is always nice. Related to booting fit images, it's not that rare that developers get confused with multiple boot commands, which is boot M, boot Z, and they're not that great documented. What is important is that there's only one command that actually verifies signatures, and that command is boot M. And boot Z and the friends do not, and they cannot be compiled out as well. So you end up with a set of commands which all of them kind of do the same thing, and they do boot your image. So people get confused and they get to use a wrong command to do it. Or, for example, there is a path in your boot script that may lead to execution of that command via some probably configuration values or some leftover development options, as I mentioned before. So what you do is you have a really close look at what the device does when it tries to boot, or better yet, you have a look at the actual boot script in the environment variables. And if it is possible to actually reach to the bootz command, you simply program a crafted kernel and init RAM disk, and you get to that bootz command, and bam, You also get to execute arbitrary code, which is great. And the last but not least probably is the fact that boot M also tends to accept unsigned images. So as U-boot is a very flexible piece of software, there is a multitude of different image types that can be supported by the bootm command, such as it could be fit images, it could be Android images, it could be legacy images, for example, raw Z image, and so on and so forth. And there is quite a few of them. These are compiled in or compiled out depending on the compile time options. So if you don't change it, if I remember correctly, they all compiled in. What is important in this case is that U-boot tends to guess the format of the image at runtime using some heuristics. So it reads the image from your storage, whatever that might be, into memory. It then applies some heuristics to see, oh, could this be a fit image? If it is fit image, then I will try to put it as fit image. Or could it be a Z image, for example? Then I will try to run it as Z image. So you see, even if you manage to use the right boot command, which is not non-trivial, as I say, the attacker could again be successful in bypassing your hardening efforts by simply programming a raw Z image and executing arbitrary code, because U-boot guesses that this is a Z image, and I was compiled to include support for booting Z image, so why don't I boot Z image? And as I say, to get to execute arbitrary code, which is always nice. Finally, U-boot also allows a rather unusual configuration where it actually builds into not one image, but two separate images called SPL and TPL. Well, SPL stands for secondary program loader, and TPL stands for tertiary program loader, of course. And this stems from a rather a technical issue where in some systems the ROM bootloader is unable to load arbitrarily big secondary program loader images. For example, it could be limited to load, say, 64K only from whatever external storage you provide. So this is circumvented by splitting U-boot into SPL and TPL. So you have SPL as a rather lean binary, and TPL to have all the functionality that you will require to boot your system and to have all the development functionalities that you would like. TPL tends to be considerably bigger, and it's not rare to see U-boot images being, for example, 500K or more. So as it goes, SPL is of course verified by the ROM code, and it is signed by the tools that the SoC vendor provides you to do it. And TPL is tasked with verification of the next stage. For example, if it is a fit image, then the stock U-boot functionality is used for that, or you could program your own verification method if you wish so. But there is a catch, and the catch is that you might forget to instruct that SPL verifies TPL. So it does load it, but it forgets to verify it, which is not very nice, and it breaks the chain of trust. So exploitation in this case is very easy again. You just program a modified TPL image and get to execute arbitrary code, which is always very nice. And these are probably the most common mistakes that we see, well, let's call it in the wild. that we see when we assess different devices that come our way from our customers. But the impact of the each and every issue is that your device security gets compromised, meaning that the attacker gets to execute arbitrary code, whether it's like once or whether it's permanent, and most often that not it is a permanent compromise. So you just pre-program the device and you get to bypass all the nice secure boot features forever. Well, at least starting from the Linux kernel. And this is important because this means that all the protections that you implement to avoid quote unquote tuning of ECU parameters gets bypassed as well, which is not that good, if I may say so. If we get to key takeaways to how and what you should do to avoid this being such a big problem, first of all, it's always good to keep U-boot up to date. Whether this be via upstream updates where you just maintain your own fork of it, or whether you just get spot patches fixing different security issues, please keep U-boot updated, as it is used in quite a few projects. It gets more and more attention from security specialists and more attention from let's call them black hat security specialists as well. So it won't be surprising if we see that with time we see more and more issues popping up, or rather getting discovered. It also helps a lot to remove extra boot options in production software, because when it gets to production, you don't really need them anymore. But it's not that rare that they also remain in the final builds. So the attention needs to be paid to that problem, and make sure that these not get carried over into production. We also recommend to use compiled-in environment in production, because frankly speaking, there is very little chance that any environment variable will ever change when your device goes into production, because by that time, everything regarding the boot process is well, it's set in stone. It won't change at all. So there is no actual need to pull it from the flash. So you might as well just compile them and be done with it. As a continuation of the previous point, it is also highly unlikely that you will ever need to interrupt the boot sequence in production. So it makes sense to actually disable that feature. For that, there is also a configuration option in U-boot 2. So even if the attacker will press many keys, the boot process will not get interrupted, which is what you want. It also helps a lot to avoid fail open conditions by making sure that the boot process restarts from the beginning on failure. Because if you think about it, when you have such a situation in production environment, when you cannot boot the ECU at all, it will probably not be too helpful for the customer that they get the U-boot prompt, because they, well, in all honesty, they won't see it, because it's an ECU in a car. It's hidden somewhere far away inside the car, and there is no way that a legitimate or rather a well-behaved customer will have access to that feature. So if anything, it rather helps to make the unit restart on boot failure, and U-boot provides a nice function called reset, I believe, which does what it says it does. It restarts the boot process by resetting the device. So if there is some flakiness in the boot process, this will, if anything, ensure that something good might happen, or the device might magically boot. But in any case, it's not a good idea to allow to fall through and enable the console. It also probably wise to use signed fit images because, first of all, it is something that comes with U-boot itself out of the box. So it is rather well supported in terms of security as well. And it helps to uphold the chain of trust that is pretty much a requirement these days, that each and every ECU has to have some kind of security scheme implemented to prevent raw code running on it. So fit images provide a rather straightforward way to do it. You just follow the documentation, however well written it might be, and you end up with a secure system. If you remove support for unused image formats, of course. And that is something that is done in the configuration menu. So just disable the ones that you do not use. For example, Android and legacy images are, or rather will not be used if you choose to use fit images. So there is no reason to keep them around and have them take the precious boot memory on the flash. And then again, if you choose to use signed fit images, you would also want to make sure that you use bootemp for booting them, because only then you will receive the benefit of your signatures being actually verified. And speaking of verification, you would also want to make sure if you have to use TPL, that it is also verified by SPL during the boot process, because otherwise your chain of trust will be broken and the attacker will be able to compromise the device. Finally, last but not least, you can read the full white paper at this URL in case you want to get into more detail on any of these issues, or if you want to have more insight into how to implement these key takeaways, please go ahead and read the white paper. It's free of charge, of course. And if you have any questions regarding the white paper, still, you can always reach out to myself or to the product security team at F-Secure, and we'll be happy to consult you on any of those problems. Well, as it happens, we have reached the end of the presentation from my side, and I think if there are any questions, I will be happy to answer them right now.
Okay, so at first, very thanks from my side to share with us this information and also the knowledge behind. I would like to start with the first question. If in a product development, the measures you mentioned during your presentation will not taken care, what from your perspective would be, if we think from an attacker perspective, the easiest damage or the easiest way to make a damage which an attacker can reach, and what would be, from your perspective, the most critical damage an attacker can reach by using these weaknesses?
I see. So if you consider that there is more onboard computers with each new model of the car, of course, and all these computers tend to be networked, right? So if you manage to gain access to one of them, even temporarily, right, and if you find out that this component, this ECU, fails to implement security precautions that we have outlined before, and this means that the attacker is able to compromise such an ECU permanently, which means that they will regain access to this ECU and to your automotive network, even if you turn the power off and on again. So it will just restart the computer, and since U-boot is already compromised, then the attacker will be on your network again. If anything, this is the golden dream of any red teamer person. If you know what I'm talking about, you just gain persistent compromise of a unit. Of course, it depends on which exact unit it is, since modern car networks tend to be segmented. But it is probably the worst thing that can happen to an ECU. So the attacker will be able to override anything that happens after you boot in terms of software.
Okay, thanks. A second question, if you compare the measures to make the boot sequence secure with other measures, for example, to secure the diagnostic accesses and so on, or make the flash process secure somehow. Do you think that this U-boot startup sequence securing is one of the basic measures that you should take care if you develop such a kind of an ECU, or do you think there are other measures which should be in place before you start with this kind of measures?
I think that's a good question, and it touches on the question of prioritizing the development effort.
Yes.
I would say it's not a question of which comes first, but it doesn't really matter which one you implement first and which one you implement second, right?
Yes.
But it has to be the case that they both are implemented. So you cannot have secure U-boot without having a secure root of trust, secure boot implemented in the SoC that you use, because then the attacker will just overwrite the U-boot and that's it, right? And similarly, you cannot have a secure Linux environment without having a secure boot and so on. And if you follow the chain, it terminates in actually the update process, where you cannot really have a reasonably secure update process if you don't have a secure root of trust in place. Because suppose your update process goes through and everything is good, and somehow the attacker is able to pass the right image to the unit, right? Which they crafted because they know the secret password or secret key generation algorithm that is used in UDS that you implemented. And then if you don't have a secure boot in place, or if you don't take care of a securing your boot environment, the crafted image gets to boot because there is nothing to restrict them, right? Compared it to the situation where these restrictions are in place, even if an attacker is able to bypass your UDS authentication, your update mechanism authentication, for example, if you sign your update package in some way, and then if signature is valid, then you proceed with the update. Otherwise, it's just aborted. Even if they are able to bypass these measures, and if they are able to program their fake update into the ECU, then they get stopped in their tracks by the verification that happens during the boot process. So they also have to know the secret keys that are used to sign your software, which gets to actually boot not the update package, but the actual bootloaders, the kernels, and so on. And it is highly unlikely that they will know this key. So if anything, I would say that these are not separate measures, but they act together as pieces of the same puzzle to make sure that your device is secure at all times.
Yeah, I absolutely agree. So that's also a little bit related to the old known game here that from a developer perspective, we have to take care about the whole system to make it so hard as possible to come during one backdoor, right? And an attacker would be very happy if he found one backdoor which he can use to enter the system, and then he's just finally happy. And
You're absolutely right.
yeah, and if you not take care about every possible door, I would say, yeah, then it's hard to guarantee that if the product is in the field, nothing will happen.
Exactly. That is why it is wise to adopt the security in depth approach and try to introduce as many layers of security that you can possibly do within reason, of course, but still. So if any one layer fails, that you have some safeguards in place that preclude the attacker to move from moving forward.
Yeah, that's also right. Okay, so I at the moment I don't see more questions in the chat. So I think your presentation was very well prepared, and you
Thank you very much.
told everything
And
what is related.
well, if anything, this just touched on the most important or rather most often seen problems that we advise our customers on. There is also implementation problems that you have a programming error in something that you written to extend your boot and so on. But I thought that these are less relevant because it should be obvious that this could happen at any point, of course. But I just wanted to say, if anyone has any questions, they are very much welcome to reach out via Twitter at InfoSecDJ at any point, and we will have a nice chat.
Okay, so one additional question comes in now, so I would take the chance to ask you about that. And it was about U-boot environment variable encryption is deprecated recently due to a vulnerability in their AES encryption. I hope you are aware about it, but the question is, what do you recommend to secure it?
The best approach to secure it is probably not to use it. As I said, there is no really good reason to have a mutable environment variables in place when you hit production. If you actually think you need it, then you might want to reconsider your implementation approach to whichever feature you think that needs it. Maybe there is something else that fits the bill better. But if you are left with no options but use it, I think it's probably best to roll your own solution in this case, because what U-boot offers at the moment is a little bit broken.
Mm-hmm. Okay, so thanks to share us your thoughts about this as well.
It has been my pleasure.
So then I would say we come to the end. I would give you additional chance to say some final words from your perspective to the audience.
Well, my final words will be, don't be scared to use U-boot. It's a great piece of software. By all means, do use it, but take care to not use it blindly. Take care to secure it properly as you would secure any other piece of software that runs on your system.
Okay,
and
so
that will be it from my side.
Okay, again, thank you very much to be with us today and share this presentation and your knowledge with us. From my side, also to the audience, thank you very much for being with us today. I hope you enjoyed this session as well. I hope we see us during the next weeks again in one of our upcoming topics. I hope you are interested in as well. And then from my side, have a nice evening, a nice afternoon, or maybe also a nice morning wherever you live in the world. Thank you for being here, and Until next time. Bye bye.
Thank you, everyone, and bye. Take care.
Okay.